Hey everyone, in this video we're going to learn about geometric sequences. A geometric sequence is a sequence in which the common ratio, r, is multiplied to each term to get the next term in the sequence. An example is the sequence 3, 6, 12, 24, 48, continuing on. If we compare one term to the next, well 3 to 6 we'd have to multiply by 2, 6 to 12 we'd have to multiply by 2, then 12 times 2 is 24, 24 times 2 is 48. So the common ratio of this sequence is r equals 2. Right, to go from one term to the next, we have to multiply by 2. Now if we look at the definition again, it only includes multiplication, but division would be included as well. Division is just multiplication by a reciprocal value. Right, so if we were dividing by 3 to go from one term to the next, we could just think of that as multiplying by 1/3. Okay, so any sequence where we're multiplying or dividing to go from one term to the next is a geometric sequence. Now determine if the following sequences are geometric. If they are, state their common ratio. So they've given us 4 sequences, and we're trying to figure out which ones are geometric and what the common ratio is in the geometric sequences. So the first sequence they've given us, 7, 10, 13, 16, 19, continuing on. Well, looking at the terms that they've given us, it seems that it's going up by 3 each time. Right, and I can verify that. 7 plus 3 is 10, 10 plus 3 is 13, 13 plus 3 is 16, but I'll stop writing because since we're adding to go from one term to the next, this is not a geometric sequence. Not geometric. In this case, it's an arithmetic sequence. The next sequence they've given us, -3, 15, -75, 375, -1,875, continuing on. Okay, so the fact that we're going from negative to positive from term to term means we definitely have some sort of multiplication happening. We wouldn't be able to do that by adding or subtracting the same amount each time. So let's see. To go from -3 to 15, we'd multiply by -5. And then 15 times -5 is -75. -75 times -5 is 375. And 375 times -5 is -1,875. Now if you don't trust me, you can always plug that into a calculator and do this multiplication out to see that if you take one term, multiply by -5, you would get the next. So we have a common ratio here, so this sequence is geometric. And the common ratio is -5. Our next sequence, 1, -4, 16, 64, -256, continuing on. So looking at the terms, it looks like we're multiplying to go from one term to the next. So let's check this one out. So 1 times -4 would get us -4. -4 times -4 would be 16. But then to go from 16 to 64, that would be times 4, not times -4. Well, that's an issue. A geometric sequence, we need to be multiplying or dividing by the same value to go from one term to the next. So because of this, this sequence is not geometric. So now the next question is, could it be arithmetic? But the answer there is no. Right, to get from 1 to -4, we would subtract 5, and then -4 minus 5 is not 16. Okay, so this is neither arithmetic nor geometric. It just happens to be a random sequence that they've given us. The last sequence, 6, 3, 3/2, 3/4, 3/8, continuing on. So looking at the terms here, it looks to me like they're multiplying by 1/2 to go from one term to the next. So let's verify that. So 6 times 1/2 is 3. 3 times 1/2 is 3/2. And then 3/2 times 1/2 is 3/4. 3/4 times 1/2 is 3/8. So we do have a common ratio to go from one term to the next. So we have a geometric sequence whose common ratio is 1/2. So one thing to point out, in the future, one of the challenges that we're going to face is being able to look at a sequence and decide whether it's arithmetic or geometric. Right? In this case, we were just focused on figuring out the geometric sequences. Okay, but in the future, we're going to have to decide, and then based on our decision, write either a recursive or an explicit formula. Speaking of explicit formulas, we need to figure out how to write one for a geometric sequence. In order to do that, let's answer this question. What type of function increases or decreases by a common ratio over equal intervals? So essentially, to go from x equals 1 to x equals 2, in this function we'd be multiplying. Well, that would be an exponential function. Exponential function. Right, think of y equals 2 to the x. 2 to the first was 2, 2 to the second was 4, 2 to the third was 8. Each of those outputs we multiplied by 2 over a distinct x interval. Now another reason exponential functions are going to make sense here, an exponent is just condensing repeated multiplication. Well, isn't that how we're finding the terms of a geometric sequence? Repeated multiplication? In that last example, we were multiplying 1/2 over and over and over again. So that's another reason why exponential functions are going to work very nicely for setting up an explicit formula for a geometric sequence. Now a standard form of an exponential function, if we recall, is y equals a times b to the x, where a was the initial value or the y-intercept, and b was the base of the exponential function, essentially our common ratio, what we were multiplying by each time. So if that's the case, which of the above variables represents the common ratio? Well, that would be the base of the exponential function, which is b, or the base. So a geometric sequence can be modeled by an exponential function with a domain of whole numbers. We've already made the connection between geometric sequences and exponential functions on the previous slide. Including a domain of whole numbers, well, remember, sequences typically have a first term, second term, third term, fourth term. There were a few sequences that we had a 0 term, first term, second term, third term. To cover all of those sequences, a domain of whole numbers is the most appropriate. Also from the last slide, the standard form of an exponential function is y equals a times b to the x. Remember, b is the base of the exponential function, a is the y-intercept, or the initial value. If we plug x equals 0 in, our y value would be a. Now if we rewrite this using our sequence notation, subscript notation, we would create the explicit geometric formula. So we have a sub n instead of y equals a sub 1, the first term of the sequence, times r, the common ratio, is now the base, to the n minus 1. Well, that exponent is a little different. Why was it not just n? Where did the n minus 1 come from? And it's important that we understand it. So the best way is with a little investigation. So let's say we did just create the formula to be a sub n equals a sub 1 times r to the n. Right, we just took everything in the exponential function and we rewrote it using sequence notation. Well, if we plugged n equals 0 in, we would have r to the 0, which is 1, times a sub 1, which is a sub 1. Now that doesn't look right. Remember, this should be n comma a sub n. So if this is a sub 1, this should also be 1, not 0. Okay, well, that's a little bit of an issue. How can we alleviate that issue? Again, we know the point should be 1 a sub 1 from how we've written the terms of a sequence as a point. Right, n equals 1, a sub 1 is the value in the sequence. Now, go back to transformations. Transformations allowed us to move things left, right, up, down. So we can apply a translation here to move the point 0, comma a sub 1 to be the point 1, comma a sub 1, which is the correct point that we've been using. Well, how are we going to do that? Well, a translation of 1, 0 would accomplish that. If we add 1 to the x value, which in this case is the n value working with sequences, we would move this point to be the correct point at 1 a sub 1. Now, what effect would that have on the formula? Well, we'd have a sub n equals a sub 1 times r. Well, if we're adding 1 to the n value, then in the equation we do the opposite. So we subtract 1 from the n value. N is up in the exponent, so we have n minus 1 as the exponent in our geometric formula. So that's the reason why it becomes n minus 1, so that we get this point, 1 comma a sub 1, which is the point we know, should represent the first term of the sequence. Okay, so we're tying in a little bit of old stuff with our transformations here, but most importantly is focusing on this formula. A sub n equals a sub 1 times r to the n minus 1. Now, the best way to get more comfortable with this formula is to use it. Suppose a geometric sequence has a common ratio of 2 and a first term of 11. Create an explicit formula to represent the value of the nth term of the sequence. Okay, so writing it out mathematically, common ratio of 2, that's r equals 2. The first term of 11, so a sub 1 equals 11. We could write this as the point 1 comma 11. It's not as helpful here as it was when we were writing arithmetic sequences out. So now our explicit formula is going to be that exponential formula, a sub n equals a sub 1, the first term, which is 11. The base is going to be the common ratio, which in this case is 2, to the n minus 1, because if we're using a sub 1, we have n minus 1 as the exponent. Use the explicit formula to find the value of the sixth term of this sequence. Okay, so the sixth term, that's n equals 6. So we're going to plug 6 in for n, so a sub 6 equals 11 times 2 to the 6 minus 1. PEMDAS says we do that subtraction up in the exponent first. So 11 times 2 to the 5th. Let's fix that. It doesn't look that clear. Two to the 5th. So a sub 6 is 11 times 32. So 32 times 10 is 320. 32 times 1 is 32. So we have 252. So a sub 6, the sixth term of this sequence, is 252. Write an explicit formula to find the nth term in the following geometric sequences. Assume n is greater than or equal to 1. So both of the sequences they've given us here were ones that we've already identified the common ratio of, which helps us out a little bit. So this first sequence, we identified the common ratio to be -5. And we can verify that again. To go from one term to the next, we need to multiply by -5. The first term of this sequence is -3. So the explicit formula, a sub n, equals the first term is the coefficient, so -3. The common ratio is the base to the n minus 1. We want to translate our exponential function so that this coefficient is the first term. So move it 1 to the right. Our next sequence, we identified the common ratio to be 1/2. The first term is 6. So the explicit formula, a sub n equals, the coefficient is the first term, 6. The common ratio is the base, so 1/2, to the n minus 1. Now hypothetically, I really could use any of these terms that they've given us. So let's just say I use 3 as the coefficient. Well, that's the second term. So my exponent, I would need to move it 2 to the right, not just 1, so it would be n minus 2. And that's an idea that we're going to look at more in depth in the next video, but might as well mention it here. Write an explicit formula to find the nth term in the following recursively defined geometric sequences. Assume you are given the initial term of the sequence. So the first recursively defined sequence is a sub 1 equals 5. A sub n equals 10 times a sub n minus 1. Okay, so the first term is 5. And if we look at the second equation here, I'll put a box around the a sub n minus 1. So it's saying to get the next term in the sequence, multiply the previous one, a sub n minus 1, by 10. So multiply by 10, we would get 50. Multiply by 10 again, we would have 500. Multiply by 10 again, we would have 5,000. Multiply by 10 again, we would have 50,000. and then that sequence would continue. We didn't have to write these terms out, but I think it's helpful to do so. So now we want to write the explicit formula. So a sub n equals, well, the common ratio in this was 10. The first term was 5. So we have 5, and the base is 10 to the n minus 1. Our next recursively defined sequence, we have a sub 1 equals negative 12. A sub n plus 1 equals 1/4 times a sub n. Okay, so our first term is negative 12. And then we're going to multiply the previous term by 1/4 to get the next term in the sequence. Right, that's the relationship between a sub n plus 1 and a sub n. So multiply by 1/4, we would get negative 3. Multiply by 1/4 again, we'd have negative 3 over 4. Multiply by 1/4, negative 3 over 16. And by 1/4 again, negative 3 over 64. Those would be the first 5 terms of the sequence. So the first term, it's already up here, but it doesn't hurt to rewrite it. A sub 1 equals negative 12. The common ratio, which we identified from the other equation, was 1/4. So the explicit formula here, a sub n equals negative 12 times 1/4 to the n minus 1. And there we have our explicit formula for this sequence, which they gave us recursively. Write a recursive formula for each of the following explicitly defined geometric sequences. Assume n is greater than or equal to 1. Our first sequence is a sub n equals 8 times 5/4 to the n minus 1. This is exactly the form that we've been working with. So identifying the pieces, the base of the exponential function is the common ratio. So r is 5/4. And then because the exponent is n minus 1, our coefficient is the first term. So a sub 1 equals 8. We can confirm that by plugging in n equals 1. 1 minus 1 is 0. 5/4 to the 0 would be 1 times 8 gives us 8 as the first term. So having these two pieces of information, we can list out a few terms of the sequence. Even though they don't ask us to do that, it could be helpful in creating that recursive formula. So our first term is 8. Multiplying by 5 over 4, so 8 divided by 4 is 2. Times 5 is 10. Then multiplying by 5 over 4 again, so 10 divided by 4 simplifies to be 5 over 2. Then times 5 would be 25 over 2. Multiplying by 5 over 4 again, we get 125 over 8. And one more time, multiplying by 5 over 4, we would have 625 over 32. And that sequence would continue. Now we can define the recursive formula by identifying the first term of the sequence, which we've already done, and defining the pattern. And we're going to use 2 consecutive terms of the sequence. Typically, we either use a sub n plus 1 and a sub n, or a sub n and a sub n minus 1. So our recursive formula will start by identifying that first term, the starting point. So a sub 1 equals 8, and then I'll use a sub n plus 1 here. So how do we get from one term to the next? We're multiplying by 5/4. So this would be 5/4 times the previous term, which is a sub n. So here we have our recursive formula for the sequence we were given explicitly. Now looking at our second sequence, a sub n equals 7 times the quantity negative 1 to the n. Okay, so the base of our exponential function is still the common ratio, so r equals negative 1. But because the exponent is not n minus 1, we need to plug in 1 to figure out what our first term is. If we plug in 1, we'd have negative 1 to the first, which would be negative 1, times 7 would give us negative 7. So our first term of this sequence is negative 7. Notice that is not the coefficient, but that is because the form is different. Our exponent is not n minus 1. So listing out a few terms, negative 7 is the first term. Multiply by negative 1 would get positive 7. Multiply by negative 1, we have negative 7. Multiply by negative 1, we have positive 7. And then negative 7, and that would continue. So this is an alternating sequence, and it alternates between two values, negative 7 and positive 7. So we can define the recursive formula for this. So our first term, a sub 1 equals negative 7, which we already had there. And then we need to define the rule to go from one term to the next. So in this case, I'll use a sub n, and to get to the next term from the previous term, we're multiplying by negative 1. So this is negative 1 times the term before, which is a sub n minus 1. And here we have the recursive formula for the sequence we were given explicitly. Write both an explicit formula and a recursive formula to find the nth term in the following geometric sequence. Assume n is greater than or equal to 1. So we're assuming that this is the first term, not the 0 term. That's what it means when I give you this piece of information. Okay, so looking at this sequence, it definitely is geometric. It has a common ratio of 3. And we're multiplying by 3 to get from one term to the next. Let's just make sure it works for all the terms they gave us. Right, sometimes they change it up on that last term. It's not the nicest thing to do, but something we have to watch out for. Okay, so explicitly, our common ratio is 3. Our first term is negative 1. So a sub n equals negative 1 is the first term. The base is the common ratio, so 3 to the n minus 1. Right, move everything to the right one so that this is the first term. Recursively, our first term is negative 1. And then how do we get from one term to the next? We multiply by 3. So a sub n is 3 times a sub n minus 1. A sub n minus 1 being the term before a sub n. Okay, so again, to emphasize the use, explicit formula is really useful if we want to find the 50th, the 100th, the 1000th term of the sequence, because all we have to do is plug that n value in. Recursive is really good if we want to know what the first term is, they give it to us, and what the pattern is. I can look at the second equation and notice, oh, I'm multiplying by 3 to get from one term to the next in this particular sequence. So each has their advantages as well as their disadvantages. So most importantly, make sure you're comfortable writing the explicit formula of a geometric sequence before moving into the next video. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.